Cool. And then I can also give you a host as well. Okay. Make you co-host. And how do you do like question answering? So do you make some pause in the middle, or do you want us to wait until at the end of the presentation? Then you take, yeah.
Yeah, I may have a small kind of stop in the middle of the talk. Yeah, and then like most of the time most question will come to the end, I guess. Yeah.
Yeah. And I know like you have to run after 5 p.m. in Central Time, right? So yeah,
Yeah.
we'll let you go on time for sure. Yeah. So make sure all the questions can be answered on time. And did you also get the link for the Slido link? So some shy people also share ask questions over this Slido. So I can share this link in the Zoom chat, so you can click it.
Oh, okay. Let me see.
Or I can read questions for you as well. Either is fine.
Oh, I see. Okay, I see. Okay, I guess like maybe you can like tell me like what is asked.
Awesome. Great. Then let's get started. Yeah. So first of all, here's a little background. So when it was like a 2017 or 18, when this paper, like man also likes shopping, I got shocked because that paper first time made me to think about this gender bias issue or ethical issues of neural network. So that was like a breakthrough, like for me, like, oh, this kind of bias exists in the data set, as well as this bias amplified when you train your neural model. So that was a really big moment for me personally. And then after that, I became like a big fan of you. And
thank you.
kept tracking your work on the gender bias or other applications and the other the perspective as well. So we're really big fan. And even our group meeting and reading group meeting, we have read a couple of your papers as well. So I'm so excited, yeah, to invite you in our NLP class. And let me give you a official introduction. Okay, so Dr. Jieyu Zhao is a postdoc, a researcher at University of Maryland, working together with Professor Hardeman. She obtained her PhD from the Department of Computer Science at UCLA, where she was advised by Professor Kai-Wei Chan. Her research interest lies in the fairness of machine learning and NLP models. Her paper got the UMD Best Long Paper Awards 2017. So this is the paper that I mentioned. And she was one of the recipients of 2020 Microsoft PhD Fellowship and has been selected to participate in 2021 Rising Stars in ECS workshop. Her research has been covered by news media such as Wires, the Daily Mail, and South China Morning Post. She was invited by UN Women Beijing on a panel discussion about gender equality and social responsibility. And you can check out more information about her in her homepage. Okay, so let's give a big applause for today's speaker, Jieyu. Yeah, and then it's all yours.
Okay, thank you. Okay, thank you for the nice introduction, and thank you everyone for coming today. So yeah, I'm going to talk a little bit about my work on building accountable NLP models on social bias detection and mitigation. So basically, it's kind of the talk is kind of formulated kind of from my job talk. So we will have like maybe more kind of breadth, like a little bit kind of depth. So if you have questions, like we can have like more discussion, I guess more technical discussion in the end. Yeah, okay, cool, let's get started. So yeah, so nowadays we know that our natural language processing, those models, they are extremely prevalent, and they are impacting our daily lives in various ways. For example, we are already very familiar with the chatbot, the personal assistant, and the recommendation systems. Also, during this COVID-19 time, many NLP researchers build the search and the retrieval systems to help our doctors. So with recent advanced machine learning techniques, now the NLP models can show really good performance. And one example is in the co-reference resolution. So this coreference resolution task is very important in the NLP domain. And the goal is to extract all the phrases referring to the same entity in the given text. It's one essential step for many higher level NLP tasks involving in the natural language understanding, for example, in the document summarization, question answering, or information extraction. So here for the example about the short ball about Paul Allen here, a deep neural network model can identify that all the blue ones refers to the same person, Paul Allen. The pink one refers to the location, Seattle, and the cyan one refers to another person, Bill Gates. So now the models can process the text and extract the complicated correlations automatically for us. So the performance of the graph model has developed significantly in the past few years, as shown here. The x-axis is the time and the y-axis is the model performance in the F1 score. So the higher the better. So over the past decade, the model performance improves from around 54% to nearly 80%, which is a great achievement in our domain. Okay, so another example about the astonishing performance in the NLP domain happens in question answering task. So for this task, we need to answer some questions based on the given paragraph. And nowadays, existing models, they can even do a better job than human beings, like shown in the first row. Here, the human performance means the inner agreement between human annotators on this benchmark dataset. So the result here is really excellent. It tells us now we can build the AI models to do some tasks for us, and they can even do it better than ourselves. Also, such revolutionary achievement in the NLP system happened especially during the past few years, thanks to the rise of those pre-trained models. So each year we have several new models created, and they are becoming more and more powerful. So we now have entered a very exciting area that we can tackle many NLP problems we used to think very difficult. And a lot of attention has been attracted to this research direction. So are we good now, since now we already have so many powerful NLP models as shown on the last slide? Well, most of the time we train and evaluate an NLP model based on some benchmark data set. And the existing models, they can do a really good job on this data set, as I showed previously. But when we use those models in the real applications, that usually just come the heartbreaking moment. So keeping scaling the model size is not enough. We are still in the middle age, or more pessimistic, the early age of achieving the accountable NLP models. And there are several issues people have identified in modern AI systems. So for me, in my research, I focus on detecting and mitigating social biases in NLP models. So by social bias, I mean that machine learning models produce the results that are systematically prejudiced in favor or against a certain group of people. For example, it's related to like the individual, the group, or the characteristic that is considered to be unfair. For example, it may be related to the gender, race, ethnicity, etc. In the following, let me show you a few familiar examples of the current NLP system, especially in the context of this social bias. Okay, the first example I show is still coreference model. So a coreference data set. So we will talk about this task previously. So like in this case, for the sentence on this slide, a model can successfully identify that the president and his refer to the same person in the real world. Okay, if a model is accountable and does not make any gender biased decisions, it should make the same prediction very easily when we change the pronoun from his to her. But unfortunately, in this paper, we show that the coreference link between the president and the female pronoun breaks. And similarly, the model fails to correlate females with certain occupations, such as lawyer, programmer, or doctor, which in return will also affect the real world applications built on this technique. So to better quantify the bias in coreference model, we create the window bias dataset to evaluate the bias based on the counterfactual method. So in this dataset, each sentence contains 2 occupations and 1 gender pronoun. the two occupations have different inclination to the gender. For example, the physician here is stereotypically a male occupation, and the secretary is historically stereotypes towards female. Okay, if the correct link in the sentence follow the social bias, we call it pro-stereotypical, otherwise anti-stereotypical. So the social bias can be obtained from some labor statistics. For example, the first sentence here has a link between the physician and he belongs to the pro-stereotypical set, and the following one belongs to the anti-stereotypical set. Also similar to the previous, the motivated example, if one system does not have any gender bias, the performance should be similar for the two subsets. And if a model learns social bias, it will be confused by the gender cues in the sentence. So in this case, we use the performance gap between the pro-stereotypical and anti-stereotypical data set as the metric to evaluate the bias in the correct model. So here is the result of an end-to-end deep neural network model on a window bias data set. So the green bar here, the result on the pro-stereotypical set, and the yellow one is on the anti-stereotypical set. So we are still doing a pretty good job on the benchmark data set, like the model performance is around like 68% on the F1 score, which is great. But in the reality, the model is showing a significant bias issue. It's like the delta score here. So now I show the bias in the coreference resolution. And nowadays, researchers have found social biases in other applications that can impact our daily life. For example, they have shown there are biases in machine translation, in toxicity detection, or in dialogue systems. So these biases will bring in like really big harms to our society. For example, now researchers found that a medical QA system has strong bias towards the certain race and gender subgroups, which means the patients from those groups cannot get the correct treatment. And these biases will also hinder women from getting jobs, or they can generate extremely toxic comments to certain group of people. Also, not only in the NLP domain, now the problems about the biases in AI have been recognized by the society. For example, AI was used in criminal justice, and the researchers have found the severe racial biases in those algorithms. And also about other biases in, for example, the healthcare or economic scenarios. Nowadays, there are funding calls from the government and the big companies to focus on the AI biases. For me, I was very honored to be supported by the Microsoft PhD fellowship to work on the NLP fairness problem. And nowadays, we have research groups working on those topics, and our community has created new conferences and workshops on this direction. But back to a few years ago, when I started my PhD, there were not so many discussions on this topic as it's today. And I'd like to share some of my efforts on this direction. So the research goal my research goal is to build accountable and trustworthy NLP models that could be accessible to everyone. So in fact, we as humans, we also have our own biases, but we can go to workshops or attend tutorials and change our perceptions accordingly. So I want to ask, can we do the same for all NLP models? So during my PhD life, several years ago, I have made some steps by conducting the research focusing on this NLP fairness problem. My work ranges from understanding the biases in different NLP models from different layers of the NLP model. And it covers the quantification of bias or bias amplification, as well as proposing the corresponding mitigation method. Okay, before I start the discussion on my work, I'd like to quickly recall what an NLP model pipeline looks like. So we collect the data from the real world, learn the representations, and then we conduct the structured inference, gather predictions, and we evaluate the model based on the predictions. My work touches the bias analysis from this whole NLP pipeline, and it addresses two important tasks, the bias detection and mitigation. So here's the overview of my work. my research serves as the pioneering work in the NLP fairness direction. So one of my paper won the Best Paper Award at EMLP 2017. And all the work here served the same goal, to build accountable and trustworthy NLP models. Nowadays, our community has recognized the importance of social bias issues in NLP systems. For example, the latest version of the famous NLP textbook by Professor Dandrowski and James Martin has included several sections about this problem, and it also covers some of my work. Also, paper published along this direction has also increased significantly along these years, as shown in the number of ethics NLP papers at ACL. And some of the papers cite my research work according to Google Scholar. So for me, I was very honored to be invited to join the panel discussion hosted by Yu and Wei-Ming to discuss about the gender equality and the social responsibilities. So in more details, some of my research analyzes the bias in the representations. We know that representations are very fundamental in NLP, and most of the existing work are trying to learn the representation to boost the downstream tasks. But we are the first few to understand the biases in the representations and how it will affect the downstream tasks. And also in a series of work, I put great effort in discovering a new category of bias, which we call it bias amplification in NLP. And these tasks are very challenging because now we are dealing with multiple variables at the same time, and we are able to find the good ways to calibrate the model and reduce the bias amplification. Also in my work, I try to propose new ways to define the biases in NLP, which will help us to recognize the model weakness. Otherwise, we could incorrectly trust a model without knowing the underlying issues. So my research formulates the problems in the NLP fairness direction and connect them to the existing literature, such as so that I can identify the potential technical solutions. For example, in the existing machine learning or NLP literature, people have already done a lot of work on the representations to add or remove information. And this is related to my work about dealing the gender bias from the representations. And also later in this talk, I will show you that mitigating the bias amplification is also related to the model calibration in the machine learning community. Okay, so in this paper, I will specifically actually talk about like 3 works, like I think we've seen about the reading list previously. So let's first look at the first part about the bias amplification and the calibration. So it's about like then also like shopping paper. So let me give you some idea about this paper. So let's start with my example on this slide. We have a visual semantic role labeling task. So given the image on the left, the task, we need to answer some question like what's in the image. So it's clearly this image is about a cooking activity and the food is a vegetable. So we need to also try to guess what is the agent. So as a human, the question is very easy to answer. So, okay, yes, it's a man doing this cooking activity. But with an advanced machine learning model, it tells us it's a woman. So what's happening here? So like the machine learning and NLP models are often trained on large-scale data set that usually contains biases. For example, for the data set for the visual semantic role labeling task on the last slide, the data set was collected from the web, and about 2/3 of the cookie images actually have female cookie. But more surprising that when they evaluate the model in a similarly distributed depth set, the model now predicts a more skewed results, now seeing about 84% of the cookie images have female cookie. And we refer this as bias amplification. We've done the same evaluation for multiple activities and even nouns in a different data set. So the story is the same. The underlying corpus is biased, and then the model amplifies that. So the concern is that if the model is used in the reality, it will make different predictions for men and women in the similar context. It not just duplicate an already biased view of the world, but actually further amplify that. So next, let me show you, give you some background about the data sets and the tasks we use to evaluate this bias amplification issue. So the first data set is image situ, which is the example I showed previously. Given an image or something happening, the visual semantic labeling task needs to predict a structured summary of this activity. For example, in this case, it's also about the cooking activity, and the food being cooked here is still vegetable. Some technical challenging for this task is that some values like in the image may not very easy to see. For example, in this case, the spatula is kind of obscured by the hand and the oven, and it's not very easy for us to see. So in order to predict these objects, we need to introduce the structure predictor that can use common sense about like a tool involved in cooking is usually the spatula. So how does this model work? We got an input image and we pass it through a convolutional neural network model to build the representations for this image. Then the representations is regressed to the potential values for the conditional random field model. Then we train the whole thing end to end by optimizing the likelihood under this conditional random field model. It's good for us to make some predictions using this structure predictor, but at the same, we also have worry that now we have introduced this structure predictor, a model can learn the correlations between the cooking activity and the agent being male or female. Okay, we did the same analysis on the MS COCO dataset. And this is a dataset from the computer vision community, and it's commonly used in the object detection and image captioning. So here we set up a multi-label classification task to predict whether an object appears in the image or not. And we also at the same time to predict whether a man or woman also appears in the same image. And then we use the same model structure as the previous task. So here's the data set and task we use to evaluate the bias amplification. Now it also have another question, how do we define the bias the amplification for the two tasks? So let me show you the idea on that part. Let's first define a gender ratio for an activity in the image situ dataset. So the idea is straightforward. We look at the dataset and count up how often, for example, the cooking activity co-occurs with the agent being male or female. We then compute the relative ratio of the male agent. Like in this case, the cooking activity is female dominated, so it will have a small value here. And then we also want to know how the model performs on the unseen dataset with regarding to the gender bias or the gender ratio we defined previously. So we will take a depth set, use our trained model to make predictions. And then we calculate the same ratio in the predictions as we did in the training dataset. Now in this depth set, the cooking activity has more skewed ratio than the ratio in the training set, and we call this as bias amplification. So for the, For the COCO data set, we will do the same thing as we did in this image situ data set. So just like we change the activity now to the objects in the COCO data set. So we also count up how often the male or female co-occurs with the different objects. So in this case, the snowball is male dominated, so it will have a larger value in this case. Okay, so now we have the definition, for example, for the fairness metric we use in this data set. Now let's see, other than the cooking activity I showed previously on the overall data set, how is this bias amplification issue? So here is the results on the two data sets simultaneously. On the x-axis is the gender ratio in the training set. On the y-axis is the gender ratio in the model predictions on the depth set. Okay, if a model were making exactly the same gender ratio as in the training set, all the predictions should lie on this blue line, which is y equals to x line. So here the yellow area is something we really concern, and we call it amplified zone. So basically each point in this zone corresponds to a concept that originally appeared more frequently with one gender in the training set, and the model predicts a ratio in the depth set that further increases that frequency. For example, the cooking activity we showed previously is also in this amplified zone. Okay, so overall in the two data sets, about 70% of the concepts are showing this bias amplification issue. And actually, we further look into the different magnitude of the bias in the data set, and we see that, okay, if a concept was originally strong bias in the training data set, like seeing the gender ratio between male and female is larger than 2/1, now after the training in the predictions, the model is likely to amplify the bias even more. It's like showing us the values of the bias amplification in this slide. Also, comparing between the MACQ and COCO data set, we see that for the COCO data set, now if you are looking at the strong biased concept, there is a kind of double in the amount of the bias amplification in this highly initial biased zone. Okay, so by far, the results, the analysis actually saying that with a machine learning model, it's possible that the bias in the training data set can be amplified in the predictions. So it comes naturally with one question: is there a way that we can calibrate the model predictions so that we can remedy the bias amplification? So the calibration has been a long research direction. There are several approaches have been proposed to calibrate the binary or multi-class predictions. For example, in this case, in this binary case, if we have too many positive examples, we can add more weights on the negative instances. But this calibration method is not enough for a structured case. Like in our problem, we have multiple variables at the same time, and they are relevant to each other. If we change one, it will affect the others. And also researchers have shown that it's very challenging to do the calibration under the fairness context. So it's also a big challenge for us. How can we do the calibration with multiple variables and at the same time to keep the model performance? And our idea is to use the original data statistics to calibrate and modify the model predictions at the inference time on the whole corpus level so that they are more in line with the training data set. So practically, we are going to do this using constraints, and we formulate them as the integer linear programming problem. And the advantage of this approach is that we do not need to retrain the model. And furthermore, we are going to solve this integer linear programming problem using Lagrange relaxation. And this technique will allow us to reuse the model inference machinery. Also, this technique is very general, and it's not just unique to our problem here. So this technique has been widely used in many other applications, such as in coreference resolution, and dependency parsing, and information extraction. But we were the first to adopt it to calibrate the bias amplification in the NLP domain. So how does this NLP problem look like? Well, it's going to have two parts. And the first one is to maximizing some scoring functions over the output structure Y given the image, which is the original model output. And the second part is our constraint. And it's going to say that for all the concepts, we want the predicted gender ratio to be within some margin of the training gender ratio. And the important thing to remember that the predicted gender ratio here is a function of all the model outputs on the depth set. So how does this work? Well, this is a graph similar to the previous one, training gender ratio on the x-axis and the model predicted gender ratio on the depth set on the y-axis. The dotted line here means the margin to the training ratio, and I've colored the points outside the margin in red and inside in green. So the goal of our methods is to move the predictions in aggregate closer to the solid line so that we can reduce the bias amplification. And like I said, we are going to solve this using Lagrange relaxation technique. So this technique will wrap the constraint into the inference routine and then iterate between two steps. The first one is to update how much the constraint should influence the inference time. And the second one is to perform the modified inference, hope that we find a solution to this problem. And mathematically, we can write down the Lagrangian relaxation problem like this, and alternatively update the Lagrangian multiplier lambda and the output y. So now let me show you some insights about how the methods work. So here, like, for example, we have two input images on the left. And the first one, the first step we do is we will do the inference using the original model. And maybe we get the results on the left. Now the agent for the two images are being predicted as female. Then based on the results of the inference, we will compute the Lagrangian multiplier. And based on the multiplier, we will update the potential values in our conditional random field model. And based on the new potential values, we will do the inference again. And maybe this time it will change some values of the predictions. Not like in this time, like the second image is being predicted has a male agent. Now, if the result makes the predicted gender ratio exactly as the same as training gender ratio, we can stop here. But practically, it's going to be very challenging to satisfy all the constraints we add to the model. So we will do this for some fixed iterations and then stop. So how does this method work? Well, this is the result before we do anything. It's like original model prediction. And then we see that after adopt our methods, all the points kind of scratch toward the solid blue line, and the magnitude of the bias amplification has decreased significantly. And the exciting thing here that we can do this at essentially no loss in the model accuracy. And after the paper is published, we further improve the results by exploring the different optimization methods. And we see that we can further reduce the violation ratio to about 21%, and again, at almost no loss in the model accuracy. So basically, this is like the big idea about the first paper, and also like shopping. So in this one, it is the first work to demonstrate the structure predictions can amplify the biases in the vision and language task. And in this paper, we propose a general framework to quantify the bias and its amplification. And also it's the first one to propose ways to reduce the amplification in the model. So a quick extension on this is like, okay, yeah, after finishing this work, we want to know why the bias is amplified. So the analysis we did in this paper is just we consider the top predictions. And it's possible that the bias amplification comes from we force the model to make a decision, even though the model itself is uncertain. For example, in this case, the model actually had a hard time determining whether this is a male or female kind of agent, but we want the model to give us an answer. And this can be a key reason, but in reality, the reason for the bias amplification can be more complicated than this. So based on this idea, like in this follow-up ACL paper, we are wondering whether the model prediction is less biased in the distribution perspective instead of the top prediction we did on the last paper. But things will become very complicated when we consider the probability. The first one is how we're going to define the bias from the probability perspective. Let me give you an example to illustrate the idea. So consider we have the three images on the left. They are all about the cooking activity. And for the first image, the agent is being predicted as male had a probability 0.6, and the female had the probability 0.3, and a 0.1 for the non-determined case, and so on and so forth for the other images. Okay, when we consider the top predictions, we need to pick the best prediction with the highest probability. So in this case, the predictions for image 1 and 3 will have the male agent, and for image 2 has the female agent. Therefore, the bias ratio towards meal in this case is 2/3. And when it comes to the probability, we're going to calculate all the probabilities of male versus all the probabilities of being either male or female. So in this case, the bias score in the distribution perspective will become 0.59. Okay, so now we have the definition for the bias in the distribution perspective. Now let's see how the bias amplification issue looks like in the distribution. So this is the result. The left figure is the same one like, as I showed previously on the top predictions. And similar to it, we found that the bias is also amplified in the distribution perspective on the right figure, even though it's less significant. So this indicates that forcing the model to make the top prediction does amplify the bias, but except for making the hard predictions, there are also other kind of sources causing this bias amplification, which requires further study. And also in the paper, we also want to mitigate the bias amplification in the distribution based on the posterior regularization method. And intuitively, we still want the gender ratio to be similar as the training gender ratio, but it's not just like in the distribution perspective. And similar to the Lagrange relaxation method I kind of introduced previously, this posterior regularization method is also an iterative procedure. But for the interest of time, I will skip the technical part. But yeah, we can have like some discussion in the end of this talk. So here are the results after adopting this posterior regularization method. We see that we can remove almost all the bias amplification in the distributions and at the same time keep the model performance. Okay, so in these two papers that we show that with our model, the bias is amplified in both the top predictions and in the distribution perspective. And with our methods, by adding constraints during the inference time, we can calibrate the model and reduce the bias amplification. Okay, so I think this kind of natural stop point to see if you have some like quick questions here. Yeah.
Yeah, any question? Yeah, London, you can come over here. We have some students here as well, so.
Oh, I see, okay.
We'll just come here and ask.
Hello, I want to make sure I'm understanding like the prediction versus training set bias. Is prediction like after it's trained, this is what it's actually just outputting, and how like what's the difference between the two?
Yeah. So the training is basically the general training data set. The prediction is like from the dev set. You get the dev set and you make predictions on the dev set, and you're comparing these training and these predictions.
Okay.
Yeah.
And then what's the line that's not like the exact XY line, but is slightly off? Like, why does that occur and what is that on the graphs?
Like
it's a black line.
Basically, say, okay, it's kind of regression about all the points here.
Okay.
The bias in the training versus the bias in the prediction. Basically saying, okay, yes, if you have like larger bias in the training, also kind of in the predictions, like the bias is also larger. Yeah.
Got it. Okay. Yeah. So it's slightly off from the middle one, because if you have less bias in your training set, you get a lot less bias in your predictions. But if you have a ton of bias in your training set, you end up with, or like a moderate amount of bias in your training set leads to a lot of bias in the predict. Okay. So that's the bias amplification.
Yeah.
So if that line was like tilted on the opposite side of the X equals Y line, then that would mean you had bias reduction.
Yeah.
Okay.
Yeah.
Got it. Thank you.
Yeah. Okay.
Cool. Let me just quickly check the Slido and see whether there's a question. Okay, there seems to be no question. So I have one quick question.
Yeah.
So I guess most of the model you used in this co-reference or other tasks, I guess they're fine-tuned on specific benchmark, and they use the BERT or GPT-2, whatever, right?
So the answer is no. Like at that time, there's no BERT yet.
Oh,
so,
I see.
Yeah.
Sorry. So maybe follow up that, like what if I fine tune, sorry, what if I have this large language model trained on huge language and I fine tune it on specific benchmark test sets, and then I do inference. So do you think you can keep tracking where this bias coming from? Is it coming from the low text trained for pre-training step, or is it coming from the fine tuning step on the benchmark set, or is it coming from the prediction stage?
Yeah. I think that's a great point. So actually, like my impression is like coming from like every different stage actually. So yeah, so like yeah, I think like people ever show like the pre-trained model, yeah, there are a lot of biases there in BERT model, those type of things. And also like in terms of like the fine-tuning data set, also most of the time we just collect the data set and we do not do any kind of processing to anything on that part. And also in terms of like the inference model prediction part, like we just most of the time we train those models, we just pay attention to the accuracy or F1 score, these type of things. We never consider about the fairness kind of goals. The model lacks the kind of motivation to learn for the fairness goal. So I think like all of them contribute to the final bias predictions. Yeah.
I see. And have you seen any recent work on looking at the gender bias from this pre-trained language model as well?
Yeah, actually, yeah, I think recently a lot of people actually they are doing on the pre-trained birds, those models, like they have certain kind of similar to the word embedding test set score, all those type of tasks. Like they also have sentence level for evaluating this type of thing. Yeah, this work was done like before Bert was born. So yeah.
That makes sense.
Yeah.
Okay, great. Thanks.
Okay, cool. Yeah, thank you. Okay, so in terms, I think there's another question from
How do you raise the hand?
Thanks. I have a question. Is just to your lecture, it looks like your gender bias is just a way about the bias, but we may have different kinds of bias. Does it mean current way to address bias is just try to like do some calculation on the prediction? So we try to make the statistical information for some concepts to certify the the static property, which should be just as our human common sense. If this is the framework how we handle the bias.
I'm not sure I kind of hear the
yeah,
question.
I see.
Oh, sorry.
I hear lots of noise in your background, Hauzi. So yeah, it wasn't clear to me as well.
Okay, let me just repeat my question again.
Oh, now it's much better. Yeah.
Yeah. Let me repeat my question again. Gender bias is just one type of bias. Does it? I mean, but we can encounter different kinds of bias, and we can actually usually just call anything which happens, which we made a mistake in the prediction, can be like some kind of bias of the in the data. But that after learning your framework, I mean, can we just apply this kind of framework like into other kind of bias? And also what we need to do is can borrow from your idea, just like try to do some calibration and then somehow make the statistics information in the prediction to somehow make it consistent with the statistical property of some concept in common sense. Isn't?
Yeah, I mean, like it's true. Like we have different types of biases, like different data artifacts. Like data artifacts can also contribute, like maybe model errors in the end. Like we can see, okay, it's also kind of biased towards these data artifacts. We can got that. So I think like the framework I propose here, just like one way to show, okay, one way we can use it to reduce the bias amplification in the task. And we use gender bias as my example. Is definitely you can use the same framework, for example, for the race, for the age, for other, I don't know, other kind of statistics you are kind of interested in. So I think the framework is general, but maybe one thing I want to say, okay, like when you have like multiple attributes you want to deal with, maybe you want to have like I don't know, maybe a modified version of the kind of constraint you want to add, because that you do not want to add another 10,000 constraints to your model to force the model to satisfy everything. I think it will be extremely hard. So yeah.
Yeah, actually, this is what I'm thinking, because we may observe multiple bias in the data or something, and is that possible? This kind of bias, they may have some conflicts among them.
I think that's actually possible. So yeah, but I don't have like some numbers to show you that, but I think that's possible. Like if you kind of modify kind of optimizing for one thing, maybe you can make other things worse. But yeah, just like I do not have some numbers to show you exact. Yeah,
it's okay. I'm just very curious about this question, and it's I didn't expect you can give me a very 100% answer. But yeah, thanks.
Yeah. Okay.
Thank you.
So
yeah,
maybe we only have the 20 minutes left. So maybe you can go quickly.
Okay, sorry.
And then maybe jump into the future direction. And we really like to hear about what's the next step for you to study.
Okay. I see. Yeah, I can quickly go through the other directions about the next work. Like, so, okay. So about the bias detection, like there's one example, the paper, they are trying to use machine learning and NLP technique to intervene in the hiring decision. And they try to predict the job hopping likelihood of different candidates. And in the paper, they said that, yes, and the job hopping likelihood difference is not significant between the male and the female groups, meaning there are no biases towards any gender in their system. So we really want to know, oh, is this true? Is this so good? So the thing is that actually they have similar likelihood does not mean the model is unbiased, because the model can show some differences in precision or recall. And also it's similar on the entire corpus does not mean it's similar everywhere. For example, male can have higher job hopping likelihood in education career, but lower in engineering career. They just cancel with each other. So basically this example just tell us if we do not have good ways to evaluate the model to quantify the bias, it's going to cause very severe consequences in people's daily life. So the question is like, how can we detect the biases in local region? So in this paper, we are trying to do these type of things and consider while building the automatic recruitment system, assuming we have equal numbers of qualified candidates for both genders, and we hope the false negative risks for both groups are balanced. In this case, we call it equal opportunity. So the results on the slide is very good. Now we satisfy this criteria, and yeah, we are super happy. But now if I tell you now the 4 candidates on the left are applying for HR position, and the following the other 4 are for the engineering position, definitely the model is showing some biases. So this is just like one artificial example to show the idea, but will this happen in the real data set? Basically, previously there's kind of toxicity detection task, and people found that model can identify some sentences had the word gay and label that as toxic comment. Therefore, the model will have much higher false positive rates on the sentences than otherwise. So the model can just generalize this and treat the word as a strong feature. In the end, it will just silence the discussion on those topics, even though it's a very healthy discussion. So here we are interested in knowing if there will be similar problems in terms of the race, like when people talking about different races, like Black and white group of people. And we found that a naive experiment on the 2 race groups showing there is a disparity in the accuracy about 5%, and somehow sounds biased. And then if we but we know like if we random split the kind of synthesis to 2 groups, there can also be some performance gap. So we conduct a controlled experiment to see the random split is also will introduce about 2.4% of gap, which tells us like the 5% maybe not so much bias there. But when we see like the topic is related to politics, now the gap is as large as 19%, which is definitely not cool. And also this problem is very general and especially relevant for our deep neural network model, because those models can have very smooth decision boundary and they can behave very differently in the local regions. Okay, so in this, just like to quickly wrap up this work. So in this EMLP paper, we propose clustering-based methods to detect the biases in the local region. Basically, we are trying to have an objective consist of two components. The first one is the standard clustering loss, such as the Kimi's loss. And the second one is a fairness metric. So if we're going to identify the local regions that are biased, we're basically more optimizing for the clustering loss and at the same time trying to maximizing for the bias metric, the second term here. So in this way, we can find the local clusters had the largest bias score, for example, in terms of performance gap. In the toxicity classification task, we were able to discover the local regions with strong biases when globally the bias is not significant. And also we look into those local regions, found they are related to some political topics. Yeah, so basically quickly recall like in this one, we show like bias detection is very important. Otherwise, we could incorrectly trust a model. And also we can do the bias detection in local regions. So for example, using the clustering-based methods, we can identify the local regions which are strongly biased. Okay, I will use 3 minutes to talk about the bias in the language representations, and we can go to the future directions. So currently, it seems in our existing NLP domains, English kind of dominates the whole research area, like shown in the number of kind of papers using different languages in NLP conferences. But we all know it's not true, like NLP is all about English. There are thousands of languages spoken all around the world. And nowadays, we have already done a lot of bias analysis in English. So I want to ask, how about the biases in other languages, such as languages with grammatical gender? And for these languages, most or all nouns inherently carry one grammatical gender category, and it will require the morphological agreement of different lexical categories, such as indeterminators, adjectives, and pronouns. Therefore, in this ECL paper, we look at the biases in multilingual embeddings, and we aim to answer the following questions. First, we would like to know, does the language property affect the bias exhibition? For example, the different grammatical gender systems in English and Spanish. Will this cause bias different in Spanish? And second, multilingual word embeddings align the word vectors in different languages to the same shared space. Now, we also want to know if we choose different shared space, will the bias also be different? And the third, the multilingual word embeddings enable the cross-lingual transfer learning. And then we also want to know, does the cross-lingual transfer learning also inherit the bias from the multilingual embeddings? Okay, let's see the answer. So the first one for like the different language properties. And we see the with the four languages analyzed in the paper, we see like a bias commonly across for the languages with different grammatical gender systems. And the second one, with regarding to different target space, we see that if we change the shared space, here the green and the gray bars here, the biases in different languages will actually change. For example, when we learn everything to English, the biases actually kind of increase in other languages. And also in terms of the cross-lingual transfer learning, we show in the paper, yes, the biases will also there whenever like we do the transfer learning from like one language to another language. Okay, so basically in this paper, we ask 3 questions and we see, yes, language property and the target alignment space, they will affect the biases, and the cross-lingual transfer learning will also have some issues when it comes to the bias. Okay, quickly go through the kind of future direction. So yeah, so some future plans I may consider like in a short term, I'm really interested in knowing is one is like to understand the model behaviors. So existing models, most of the time, they just make the final prediction, and it can make end users very confused, like why this is happening. But if we can make the predictions and at the same time to tell the user, oh, now your loan is rejected because you have low credit score or like the history is not long enough, that might be more acceptable to the end users. And also with this technique, we can discover some unwanted model behavior. For example, if a model said, oh, your loan is rejected because you are coming from some zip code I don't like, basically that means something's wrong with our model and we need to go back to fix that. So this one can work as an early bias detection and also provides us some information about how to fix the model. And the second one is to teach a model to understand and follow instructions. For example, the instructions can come in variations in some with some text in advance, or we can have humans in the decision loop to provide new knowledge to the model in the real time. Or maybe it's not in the natural language format. We can use some formats that are not readable to humans, but understandable to machines. And this direction can be combined with the previous plan so that we understand the bias in the model and also provide the instructions to amend that. So they both basically contribute to the final goal. How can we control the model to do the things we really want them to do? Yeah, then in the end, about the long future research direction, I feel like we have those advanced machine learning or NLP techniques. They are very important in the real world. And it's like one thing is like, how can we use those models to benefit the social good? But basically, this will require the work to basically cover the whole model pipeline. For example, existing benchmark data set might not be enough to achieve this goal. So during the data collection time, how can we, for example, dealing with the privacy issues, or is there a good way to do low cost labeling? These type of things is something really interesting, I feel. And also when it comes to the model perspective, those applications usually require the interdisciplinary research across, for example, computer vision, NLP, psychology, or biomedical domains. And also in terms of evaluating the models, which is the best metric we should use. For example, in terms of fairness itself, our community has already have many metrics defined and kind of defined there. Is there a good way to choose the best one to evaluate those high stake applications or not is something it's not very clear now. And also in the end of it, if we want to deploy those models into the real world, it's not just AI itself, it's AI, we need to coordinate between AI and many other cases. So in the end, we just want to make our model to assist humans so that they can work together to make a better world. Yeah, basically that's all I have today. And thank you everyone for listening. Yeah, and if you have questions, I guess I can address one quick one.
Yeah. Any maybe we can take one question. Any question? So by the way, the future direction seems to be really amazing. I really look forward to seeing like what comes next from your future research group. Yeah.
Thank you. Yeah.
Any question? Okay, then we can just let you go. It's right in the time. So yeah, thank you so much. It's a really nice talk and amazing research. And yeah, look forward to seeing.
Thank you.
Cool.
Yeah, sorry, I made the last two works a little bit kind of rushed, but if you have questions, just like email me. Yeah.
Yeah, and also we're gonna read your paper as well. Yeah.
Okay. Cool. Yeah, thank you.
Thank you so much.
Yeah, thank you. Yeah,
Bye,
thank
take
you.
care.
Yeah, bye-bye. Yeah, bye-bye.
Bye. Cool.
Okay.
All right, so yeah, that's all for today's lecture. And I'm supposed to give you the description of homework 4, but the department is never responding me about the budget plan. I already paid the budget, and they're supposed to give me the prepaid Amazon Mechanical Turk credit card, but still on pending. So I reminded several times, but it's a really big blocker. So once I figure this out, I will just release the homework maybe next Thursday, or maybe anytime this week. Yeah, whenever it's ready. And because we don't have much time to do the homework 4, so I'm gonna also narrow down the scope a little bit. So it's gonna be just 1.5 weeks of work. So basically collecting a few samples and no more in-depth analysis, whatever. So yeah, I would just scope down a little bit. Any question before we finish? How do you think about the lecture, the guest lecture series? Are you learning a lot or good? Yeah. And I think today's lecture was a little in hurry because she need to go before, I mean, she doesn't have time to discussion for the last 15 minutes. But yeah, I really hope to have more discussion and yeah, jumping into the lecture and then ask your questions. And I mean, this is not just a seminar, right? So we are supposed to ask questions and yeah, bother speakers as much as we can. So yeah, think about and also yeah, read the readings in advance if you can, and then yeah, write down your questions in the Slido in advance so we can yeah ask yeah more questions during the talk.
I actually had a question about the paper, but I didn't get the chance to ask it because it was sort of technical. So for the men also like shopping paper, in the paper it was mentioned that the test set has the same distribution when it comes to gender as the training set. So from my understanding, then reducing the bias amplification should improve the accuracy. But then in the findings mentioned that the accuracy or the metric, whatever they're using, roughly stays the same.
Yeah, I think their main claim is bias is amplified, and if you do some mitigation, the performance doesn't get hurt. So yeah, so I think they make a separate held out test metric to measure this gender bias, but there is still like a existing test set for SRL or whatever other NLP tasks. So their main claim is, oh, there's no gender bias in the inference time, but still it doesn't hurt the performance of original NLP or visual question answering task. So that's as far as I understand, that's the main claim. Does that make sense?
Yeah, that makes sense. I was just confused because the way they define bias, my understanding was that if the bias was amplified during inference time, then that should affect the accuracy or whatever metric they're using for the model, like the visual role learning model.
Not actually. So what if your task is co-reference? And maybe, yeah, I mean, you find a better linking between the pronouns and some occupation. Maybe sometimes it improves the performance of co-reference, but sometimes not, right?
I see. I
Yeah.
see. Okay.
And I was really wondering, like, biases are coming from this pre-trained language model or not, but actually, yeah, they didn't use the BERT at the time the paper published. So yeah, that's another I'm really curious about. Anything else? Maybe we can have some little discussion before we finish. Anything to discuss about this gender bias or other kinds of bias? Yeah, London.
I know she mentioned that the performance gap between two random groups is about like 2.4%. Is that just like a measure of how widely distributed the data set is? Like if there's a large variation in particular like small, like I'm imagining like the picture that she showed with like local areas. If those are like super duper squiggly, is that kind of what this is a measure of?
I haven't read the paper, and I think I didn't fully understand just by looking at the slides and her explanation. So yeah, we should double check the paper. Yeah. Cool. Great, and you can also check out her the homepage. I mean, she mastered this bias field. She did a bunch of like gender bias, all of her papers about this bias stuff. So if you're interested in this kind of bias of NLP systems, yeah, she's one of the rising star in the field. Yeah, so you better check out her papers. Yeah. Cool. Anything else? Okay, then we can finish early today. Yeah. Thanks for joining your class, and see you all next this Thursday. Yeah. Bye. Cool.